So today, we're going to pull back the curtain on what makes an operating system, well, operate. We're taking a tour of the engine room of what is basically the blueprint for so many modern systems, Windows NT. Let's dive in.
I mean, you've probably done it 1,000 times, right? You double-click and an app just shows up. But that one simple action kicks off this incredibly complex dance between software and hardware. We're going to follow that dance and see what's actually going on behind the scenes.
First up, we're going to look at the system's constant balancing act. How in the world does it handle sudden emergencies while at the same time juggling all the normal work it needs to get done?
Okay, picture this. The CPU is humming along, maybe calculating a giant spreadsheet. Then, all of a sudden, you move your mouse. How does it know to just drop everything and instantly update where that little pointer is on the screen? It needs a way to be, interrupted.
And that mechanism is called an interrupt. It is exactly what it sounds like. It's a signal from either hardware or software that basically yells at the CPU, hey, stop what you're doing, pay attention to this right now.
A really great way to think about this is to imagine the CPU is a person busy working inside a house. Interrupts are just urgent doorbell rings. Each one signals that something different needs attention. But of course, not all doorbell rings are equally important.
And that's why Windows NT organizes these things into a super strict hierarchy. At the absolute top of the list, you've got catastrophic hardware errors. That's not a doorbell, that's the fire alarm going off. A little below that, you have other critical things, like the system clock. And way down at the bottom are the software interrupts, which are always less urgent than a signal from the hardware itself. This whole priority system is absolutely key to keeping the computer stable and feeling responsive.
So who's actually doing all the work that's getting interrupted? This is where we need to talk about a process versus a thread. Think of a process as the whole workshop. It's the container for a program, it's got all the tools, all the resources, its own private space. But the workshop itself doesn't do anything. The threads, those are the workers inside the shop. They're the ones the operating system is actually scheduling to run on the CPU. So put simply, a process owns the stuff, but a thread does the work.
Okay, so we've got these urgent calls, we've got our busy workers. Now, something has to keep all of this organized. All the resources, every program, all the data. So let's meet the system's great librarian.
At the absolute core of the system, you have the kernel. It defines the most basic, fundamental building blocks, like what even is a thread? What is a process? You can think of these as the raw materials, like steel and wire. Then, building on top of the kernel, you have the executive. It takes those raw materials and uses them to build more complex, high-level services. It's the factory that turns the raw steel into a working engine.
But when you build a complicated factory, you can run into some really weird and complicated problems. So let's walk through a classic example. Imagine a low-priority worker thread. It's not doing anything important, maybe just tidying up some old data, and it grabs a lock on a particular resource.
Now along comes a high-priority thread. This is urgent stuff, a really critical task. And wouldn't you know it, it needs the exact same resource that our little low-priority janitor thread is currently holding.
And this is a classic priority inversion. The super important work is now completely stuck, waiting for a totally unimportant task to finish. And here's the kicker. Windows NT doesn't just fix this for you. The whole architecture puts the responsibility on developers to be disciplined and write their code carefully to make sure this kind of gridlock never happens in the first place.
So that raises the question, right? How does the system even keep track of all these different resources that threads are fighting over? Well, that is the job of the object manager. You can think of it as the master librarian for the entire operating system. It maintains one single, unified catalog of every single resource there is.
And this object manager has a few really critical jobs. It organizes everything, files, devices, even other threads, into one big directory structure. It also acts as a security guard, constantly checking who has permission to access what. And crucially, it keeps a running count of how many programs are using a resource so it knows when it's safe to delete it. And instead of giving you the resource itself, it hands you a handle, which is kind of like a coach check ticket. It's a secure, indirect way to manage access.
Now, when a thread wants to do something with one of those objects, like read from a file, it can't just go do it. It has to submit a formal request. And in Windows NT, these requests get packaged into this standard format called an I/O request packet, or IRP for short. Just think of it as the universal digital work order for pretty much any action that involves data.
Now, here's where things get interesting. Some of these work orders can be handled asynchronously.
That's where the system says, yep, got your request, I'll let you know when I'm done, and the original thread can just go off and do other things. Super convenient, right? But this convenience comes with a very, very serious danger: deadlock.
So imagine the system passes that asynchronous work order to a separate worker thread. Well, what happens if that worker thread needs a resource that the original thread is still holding on to? You get a deadlock. The worker is waiting for the original thread to release the resource, but the original thread is waiting for the worker to finish its job. Nobody can move, everyone is just stuck waiting forever. It's a perfect example of why synchronization is so incredibly important.
Okay, so a system that's just correct and stable isn't good enough. It also has to feel fast. So now we're going to look at some of the clever shortcuts and specialized parts that Windows NT uses to squeeze out every last drop of performance and make everything feel snappy.
NT has all these little tricks up its sleeves to be fast. For example, there is Fast I/O. It's basically an express lane for really common file operations, letting them bypass that whole formal request process if the data is already in memory. Then for networking, there are opportunistic locks, or OP locks, which let a computer on a network safely cache a file locally. That is a huge speed-up. And finally, there's read-ahead, which is literally the system trying to read your mind, proactively loading data it thinks you're going to need before you even ask for it.
Now, the two biggest players in the performance game are the Virtual Memory Manager, or VMM, and the Cache Manager. The VMM is the architect of memory. It manages the whole big picture, mapping each program's private little world of memory onto the actual physical RAM chips. The Cache Manager, on the other hand, is a specialist. It's the file access optimizer. Its only job is to keep copies of file data you use a lot in RAM to avoid those painfully slow reads from the disk. They're two totally separate things, but they have to work hand in hand to make the whole system feel fast.
So we have just taken a whirlwind tour of the engine room. Let's pull all these ideas together and really think about why these design decisions made decades ago still have such a huge impact on the computers we use every single day.
It's really amazing when you see how all these pieces fit together. You have interops making everything feel responsive. You have processes and threads actually executing the work. The executive and the object manager keep it all organized. Then you have specialized systems like the VMM and Cache Manager making it all efficient. And the whole thing is designed to be extended, using things like filter drivers so that, say, an antivirus program can plug right into the system. It's just a beautiful, intricate machine.
And that brings us right back to where we started. That simple, seemingly instant double-click, it's the end result of this incredibly deep, complex, and interconnected system just firing on all cylinders. And understanding a little bit about what goes into it, well, it gives you a whole new appreciation for the engineering that's happening under the hood. So, I'll leave you with this final thought. These fundamental problems, how to manage tasks, how to manage memory, how to organize everything, these are universal issues that every single operating system has to solve. How have those solutions changed over time? As you use your computer, whether it's Windows 11, Linux, or Mac OS, how can you see the echoes of these foundational decisions from NT still shaping your experience today?